Welcome to the course Digital Transformation and Technological Innovation. So, we are into our fourth module, that is Tech Advancement and Internet Basics. So, let us continue from where we left in the previous session. Right. So, we talked about the problems that are linked to silicons and the shrinking pathways, and how the overheating and cooling requirement because of the overheating and pathways getting reduced. So, size, heat, power, all those factors we discussed, and therefore, we need to look forward for innovation in chip design, so that further performance gains could be improved. So, there were certain innovations in chip designs that happened. So, we will talk about them. So, first one is multi-core microprocessors. So, multi-core microprocessor was a significant change from a single chip based CPUs, right. So, multi-core microprocessor, this is a single chip with two or more processor cores. So, earlier chips they had just one core. So, a chip having just one processor, or we simply refer to it as a single microprocessor. So, now when we say multi-core microprocessors, then there are some more two or more processing cores. So, when we say multi-core microprocessors, essentially we are talking about a single chip which is containing two or more processing cores, and that's what makes it multi-core chip. So, we are moving away from single chip or single core chip rather. So, we are moving away from single core chip to multi-core chip. So, problems linked to single core chip we have already discussed. Now, the main innovation is moving towards multi-core chips. So, that is something that happened a long time back, and this multi-core microprocessor, this multi-core chip, it actually outperforms a single speedy chip, right. And it runs cooler and draws less power, because it essentially the processing capability is now distributed across multiple chips now, and therefore there would be less load that would be taken by individual processing cores, and therefore more likely it will run cooler, and this is what happens, and will draw less power, right. Overall it outperforms a single speedy chip, right. Now, multi-core microprocessor, they have become mainstream. So, these multi-core chips, they have become mainstream chips. That means most of the computing devices that we buy nowadays, whether it's about the consumer devices from PCs, laptops to smartphones, or whether it's servers, in both cases multi-core microprocessor, these multi-core chips, they are mainstream chips nowadays. So, we have moved away from single core chips to multi-core chips, and the benefit that runs cooler and outperforms a single speedy chip and draws less power. Now, what happens to the software applications that were actually written for single core chips, right. So, that is the compatibility is inbuilt in the new architecture itself, because it is having two or more processing cores. So, to be compatible to run the software that was designed and developed for single core chips, in case of multi-core microprocessor, multi-core chips, we can use only one core at a time for those software applications. So, therefore, the backward compatibility to legacy software which was written for single core chips, that is maintained in the multi-core microprocessor. So, there is no no impact on legacy software. So, the same the new computers with multi-core chips, they could easily run the legacy software. So, no such problem there. Now, if we look at the typical core counts by device in multi-core chips. Now, these numbers are something that have been changing significantly over the years, right. So, things started with 2 cores, and then because of the same phenomena, fast cheap computing, the production technology kept on improving, and therefore, the manufacturers could pack more cores, and therefore, now what we see is that even in smartphones there are on an average 6 to 8 cores. So, we are talking about the the basic versions of smartphones. Even there we average kind of smartphones, there we see that 6 to 8 cores you would be able to see in those smartphones. And similarly, in case of laptops, the range slightly widens now from 6 to 12 cores. That means more cores would be, because laptop is something that will be proper per PC environment, and therefore the slightly heavier applications might be run on laptops. So therefore more cores would be suitable. So slight widening in the number of cores in average laptops that we can see here, 6 to 12 cores. That is something that we see in even in the average laptops. Now desktops, we see that 8 to 12 cores, right. So even few more cores in case of if we compare with the laptops, because again the desktop environment, there are more chances, even higher chances than the laptop, that some heavyweight applications might be run, and therefore packing more cores makes sense, right. So we can see clearly that core counts, they have been increasing, and now this is the average number of cores that we see nowadays, right. Similarly, gaming consoles, video gaming consoles, we talk about the Xbox or PlayStation consoles. So video gaming industry is the one industry that has benefited a lot because of the multi-core chips, and 8 cores have sort of become standard for video game consoles, and it has been like that for many years. For many years we see that Xbox and PlayStation consoles and other competitive video gaming consoles, they tend to have 8 cores or maybe more. Now top firms that are catering to this segment is Intel, AMD. So they basically they are the leaders in terms of manufacturing multi-core chips. Moving on, now come back to the point that what happens to the software. So legacy software can be run using one of the processing cores. So the backward compatibility is not a problem, as we discussed, but are we then how to take advantage of the new architecture? Can new software be written in such a manner that they can take advantage of the more processing cores that are present there, right. So that is the point here, writing software for multi-core chips, right. Now writing software which can exploit the capabilities of multi-core chip architecture, that is significantly more difficult than writing a software for single cores, right. So there are a number of reasons that we will talk about why this kind of why writing software for multi-core chips is so different. The single core program follows a predictable step-by-step path, right. So therefore everything is very well defined. So the writing software for a single core chip is much more easier when we compare this with the multi-core scenario. So let us talk about multi-core scenario. What is the problem? So first issue is serialization issue. So what happens in the serialization case? Many algorithms, they are actually fundamentally they are sequential in nature. So the way the algorithms are designed, for many cases there is hardly any change that we can do, because every next step might be depending on the output of the previous step, and there would be no scope of parallelization there. So therefore many algorithms are fundamentally sequential, so they will not benefit from the multi-core chip architecture in that sense, because of the nature of the algorithm itself, because serialization issue is there, because it is more like serialized steps in a way. So it might not be easy to split these algorithms which are fundamentally sequential into parts to run on different cores. So we cannot split the steps of sequential algorithm in such a way that we can run them parallelly on different cores. That might not be feasible itself. So this chunk of software which is of sequential nature, right, that is taken away, that cannot benefit from the benefit of multi-core chip architecture. So that is one challenge. And moving forward, then even if the algorithm can be rewritten to take advantage of multi-core architectures and some parallelization in the algorithmic steps is possible, even then there is another challenge that we refer as coordination and synchronization challenge, right. So perfect synchronization between cores is needed when multiple cores are working on the same task, and therefore they might be working on the same data. So therefore those cores need to synchronize between each other because they might be working on the same data. So there can be collisions. So perfect synchronization between cores is needed to avoid collisions when working on the same data, right. So therefore this becomes a challenge. So this will increase the overhead, right. So when this increases the overhead, then what happens to the cost of synchronization and coordination, right. So you have the multi-core chip architecture, but there is a cost that is incurred when we write software in such a manner which ensures the synchronization and coordination, but then there is a cost of synchronization and coordination, right, because we need to avoid collisions when working on the same data, right. We do not want to allow two cores to work on the same data at the same time, right. So we want to avoid that collision, and therefore cost of synchronization and coordination is going to be there, and it might diminish in many cases the targeted speed gains. So if the steps that you could parallelize were very few, and then the targeted speed gains that could be there because of those few steps that could be parallelized, if you balance that off with the cost of synchronization and coordination, then this whole thing might diminish, right. So the targeted speed gains that we might get diminished, right. So this is one key challenge that tech firms are facing when they are rewriting their existing or legacy software, or when they are writing their new software. So then they have to take a call here whether writing software for multi-core architecture, whether the gains would be there, or you are just better off with the that single speedy chip, or using just one of the cores. Then next issue is the non-deterministic behavior. So when we write software for multi-core chips, we run into non-deterministic behavior. So when we are writing software for sequential algorithms and single speedy chip, everything is predictable. What step comes next, we already know, right. So that predictability, that deterministic behavior is there. But in case of multi-core chip, and when we write a software for that, non-deterministic behavior comes in, right. So when we say non-deterministic behavior comes in, how it happens? So programs might behave differently across runs, right. Why? Because there might be workload variations, and because of the workload variations, so different tasks would be given to different cores, and those different cores, because different workload, because of the different workload that they were allocated, so they might finish their task at different times, right. They might finish their task at different times. So therefore this variation will come in, and because of that this non-deterministic behavior comes in, right. And so every time you run, things will happen slightly differently. Again the allocation might happen differently, and therefore the time taken to execute a program might not look same because of this workload variation, and which core will get what and all that, and the inherent variation in the workload themselves. So because of that, what happens? Testing of the software and the reliability becomes a challenge, right. So this non-deterministic behavior, it might throw up certain issues because different cores might finish tasks at different types. So how do we keep on coordinating and synchronizing? That becomes a challenge, and already we talked about that targeted speed gains. We need to account for the cost of synchronization and coordination, and variation in workload will actually push this problem a bit more, right. So non-deterministic behavior is there, right. However, when we talk about the new software, so these new software are more often they are being designed with parallelism in mind for performance gains, but because still if you can write good software and can take advantage of multiple processing cores, then there would be gains. So new software are often, more often than not, they would be designed and written, keeping parallelism in mind. So that has started happening. For the legacy software, it is the incremental rewriting that is happening, and and much of the legacy software are actually and much of the software is actually still legacy. In that sense, it was written for single core chips, and that continues to be the situation. So the much of the legacy software runs on multi-core processor using only a single core, right, and only the incremental rewriting is happening in practice in industries among tech firms. But a new software, people are taking conscious calls in terms of writing to take advantage of parallelism and for performance gains, right. So this is the existing situation. Then what happens to all the power that we thought that we discussed rather for multi-core chips. So OS manages that part. So there is an automatic OS handling that happens for multi-core chips, and because of this automatic OS handling, the power of multi-core chips is exploited to great extent. So what it does, modern OS actually manage multiple cores by assigning different separate programs to different cores, right. So while at the task level it might not be manageable, but at the program level it might be manageable, because OS can do this job, because OS assigns can assign different programs, separate programs to different and separate programs to different cores, right, different cores, and therefore overall computing will feel faster, because you are running multiple applications and all of them are getting executed. So despite the programs are not rewritten, most of the programs are still legacy software in a way. So still, because of this automatic OS handling across multiple cores, computing still feels faster. One example can be that we can run browser on one core, and some background updates that might be happening, that can happen on another core. So that means update is also happening at the same time, and you are using the browser. So two different cores can do these two different can manage these two different programs, right. So therefore computing will still feel faster. So automatic OS handling for multi-core chips, that is assigning different separate programs to different cores, still does the trick. Now what are the industrial implications for multi-core chips? So one point that we already mentioned, that video game console manufacturers, they were one of the biggest beneficiaries of multi-core chip phenomena, and the gaming industry really kicked off or rather got boost because of this change. So we see that late 2000s, and even from the early 2000s also, rather early 2000 itself, the video gaming took off, and they took advantage from this multi-core chip option. While we were discussing different waves of computing also, then also we noted down that same time period when this architectural change happened actually in early 2000s, and video game applications are particularly well suited for multiple cores, because in a video game there are so many things that are happening, and all those tasks can be assigned to different cores. So multiple cores can be exploited in case of gaming applications. For example, one core can be used to render the background, and the another core can be used to draw objects, right. So essentially we are talking in a gaming context, and we are thinking lots of graphics, lots of objects, lots of movement that happens in a game, right, in a game environment. So one core for rendering the background, one core, another core to draw objects, another one for object movements that would be triggered through keyboard responses or gamepad responses or mouse responses, right. So another for object movements, and yet another for communications in multiplayer environment, right. So in multiplayer environment, the players might be communicating with each other, and therefore one core can handle the communication. So that means the requirement of video game applications is actually quite well met by multi-core chips. So, video gaming industry has been one of the biggest beneficiary of this innovation in chip design, that is multi-core chips. Now, next innovation is graphics chip. So, graphics chips they are actually designed to perform simultaneous calculations necessary for image processing tasks such as animation task or AI task, right, where a lot more image data, lots of images are there, large image data sets are there, and there is a huge amount of image processing that will happen. And because different images we can process parallelly, therefore simultaneous calculations can be done. And the use case is animation AI task, where we are typically dealing with large image data sets. So, the graphics chips come to the rescue. So, this is a new design that was dedicated for these kind of tasks, for example image processing. So, what is the change in these chips? So, we earlier talked about multi-core chips for for generic CPUs, for consumer end CPUs. Now, here we are talking about the graphics chips which are built with hundreds or thousands of cores, right. So, obviously the smaller cores less speedy cores, but hundreds more of them, hundreds and or thousands of cores, because there would be large image data sets, and to be able to process them parallelly, more number of cores is something that will fit the match the requirement, and therefore graphics chip actually do quite a good job in such tasks. And obviously video game applications, they actually again benefit from this change also, because there a lot of image processing that happens in video game applications. So, video game applications benefit from both multi-core chips and also graphics chip, right. So, top firms in this market are NVIDIA and AMD. So, NVIDIA is known for known as a graphics chip firm, right, and that continues to be the case, though AMD has been bridging the gap. So, this is another innovation in chip design that is quite useful for image processing related task. Now, moving on, another innovation is AI chips. While we already talked about that graphics chips are suitable for AI tasks, because in AI task also we we work with large data sets, which could be large image data sets, and or audio data sets, right. So, in those cases graphics chip do a wonderful job, but then tech firms, they are looking to develop more specialized chips which we refer as AI chips. So, there are significant architectural changes that have happened in the design of these AI chips, right. So, AI chips, they have been designed to build chiplets. This new term is coined, designed to build chiplets, that actually reflects the the change in design that is there in AI chips. So, designed to build chiplets that connect multiple smaller chips on a single base, right. So, sort of multiple connecting multiple smaller chip on a single base, and we call that chiplet. So, that's something like that has happened in AI chip designs. So, essentially moving away from single monolithic chip designs and then having multiple smaller chips and connecting them to a single base, and we refer that as chiplets. So, that change in design has happened. So, so what can happen because of this? The separate production of compute memory and IO elements. Compute memory and IO elements can be separately produced, and then they can be linked via ultra fast interconnects, right. So, the ultra fast interconnects are being used as part of the chiplets, and the multiple small chips are there, and separate production of these can happen. So, therefore, more specialized production can also happen when we talk about the compute or memory or IO. So, that benefit will also be there, right. Top firms which are leading in this segment are again NVIDIA and AMD, which have gone for this chiplet kind of design, which has multiple smaller chips on a single base and linked via ultra fast interconnects, right. Then now what are the benefit of this kind of design? So let's discuss a few points here. So AI chips or the chiplet design that is there, it can bypass manufacturing limits on chip size, because you are taking multiple smaller chips, right, and you are connecting them to a single base. So suddenly this manufacturing limit is bypassed because of this mechanism, right. You are not going for a single speedy chip which might be slightly larger size, you are going for smaller chips. So this limit manufacturing limit is bypassed in a way, and you are in the connecting these chips to the same base, single base. So what it does, another benefit is that improves production yield, fewer broken chips. So there are advantages at the production level, and the quality of chip production will improve, because no longer you are trying to come up with single speedy chips and you have to pack in more transistors, and therefore there can be issues with respect to the quality. So because when you are managing the smaller chips, then production technology does much better job, and there would be fewer defects and there would be fewer broken chips. So the production yield would be much better. So that is another benefit that supports the benefits, supports these manufacturing firms. Now what else? Enables massive increases in transistor counts, right. So because there are multiple smaller chips that we are connecting. So through these multiple smaller chips, we can in each of those chips we will be having lots of transistors put together, add them together, and there would be massive increase in the transistor counts. So because we are connecting multiple smaller chips, so therefore the transistor counts can still go massively up, right. So one example is 208 billion in NVIDIA Blackwell chips. So there are these 200 million transistors are there. So all these benefits can be seen. Now next is few more improvements in the AI chip, but that maybe we will discuss in the next session. What we'll do, we'll do a quick summary of what we discussed in this session. So we started talking about the main innovation that happened in early 2000s, that was multi-core chips. And so multi-core chip is a move away from a single core chip and move towards two or more processor cores. And it was found that multi-core chips they outperform single speedy chip and run cooler, draw less power, and they have become mainstream since then. And older software, legacy software, not a problem, because they can just use a single core to run. And then we talked about in the current market scenario, what are the kind of cores that are there in average smartphone or average laptop or desktop. So we can clearly see that 6 to 8 or 6 to 12 and 8 to 12. Again, this data was fetched or retrieved using generative AI, some approximation, but it gives us the picture. Xbox, PlayStation also 8 cores. Then we talked about the writing software for multi-core chips, how the software to be written so that it is able to take advantage of multi-core chip architectures. Then we discussed few issues, for example serialization issue, that algorithms can be inherently sequential. So therefore it might be difficult to parallelize such algorithms, and it might become a challenge to take advantage of multi-core architecture for such algorithms. So that is one. Then the second is let us say you can parallelize algorithms. There are steps which can be parallelized. Then but then because different cores would be assigned different tasks, or they might be working on the same data. So especially if they are working on the same data, then we will have to coordinate and synchronize. So coordination and synchronization cost will also be there. So we have to do a trade off, whether targeted speed gains that we are getting and the cost of synchronization and coordination that is getting added up, whether we still are left with some speed gains or not. So that is another challenge. Then there can be non-deterministic behavior, because different cores assign different tasks and there would be variation in those workloads linked to those tasks, and one core might finish the task waiting while other cores are still continue to execute their workload. So therefore, in every run different kind of timing can be there, different time kind of variation in the execution time can be there because of this non-deterministic behavior. So therefore, testing and reliability of the software becomes a challenge, right. Then we talked about still new software is while it is being rewritten to keep parallelism in mind, but legacy software incremental rewriting is happening. Then we also talked about the automatic OS handling, which takes advantage of multi-core chips in a default kind of scenario where it allocates different programs, different separate programs to different cores, and therefore computing will feel faster because of that handling. Video game applications, they benefited a lot. Graphics chip, another innovation that also benefited the video game applications, animation, AI tasks, because there are hundreds or thousands of cores and image processing scenario. This could be very beneficial, right. Then we started our discussion on AI chip, which will continue in the next session. Thank you.